Welcome to this presentation by Tom Buchholz. This presentation discusses the tiny and the vast, predictions about elementary particles, dark matter, and the cosmos. Some results that I present include suggested predictions for new elementary particles, explanations for effects and data that people associate with the term dark matter, and explanations regarding eras in the evolution of the universe. People have pursued each of those three challenges for at least 80 years. My work seems to suggest that it might be hard to meet any one of the challenges without meeting all three. I discuss modeling underlying those results. I discuss other results of my work and that my work might help people achieve. This presentation discusses highlights of my work. For further details and information, please feel free to look at my websites or to contact me. My work suggests an analog, for elementary particles, to the periodic table of chemical elements. The periodic table shows organizing principles, such as atomic number. The table also alludes to properties, such as types of chemical reactions. The table does not show fundamental constituents. Each of most, if not all, of the blocks associates with more than one isotope. My work suggests this table of elementary particles. Here, I show all known particles and some particles that other people suggest. The column with label sigma equals 2s provides a spine. Here, s is the spin, as in the physics expression s times s plus 1 times h bar squared. The table shows so-called subfamilies of elementary particles. All particles to the left of the spine have positive mass. Some of those particles have zero charge. All particles to the right of the spine have zero charge. Some of those particles have positive mass. Some elementary particles appear, in today's universe, as far as people know, only in protons, neutrons, and other hadron-like particles. The name for each subfamily consists of the number sigma followed by a letter. Let's talk about each row. The row for which the spin is 0 includes the 0H subfamily. The subfamily contains just the Higgs boson. The 0I subfamily would contain just the so-called inflaton that some people say played roles early in the history of the universe. The next row alludes to, exactly, all known elementary fermions. From left to right, there are 6 quarks, 3 charged leptons, and 3 neutrinos. In the spin 1 row, the 2W subfamily includes just the Z and W bosons. The 2U subfamily includes just the 8 gluons. The 2G subfamily includes just the photon. Some people suggest that nature includes gravitons. The chart shows a place for a so-called 4G subfamily. My modeling outputs so-called solutions to mathematical equations that match all known elementary particles and suggest elementary particles that people have yet to find. The suggested particles associate with the following subfamilies. The 0I subfamily includes just the so-called I particle, or the would-be inflaton. The 1R subfamily features so-called arc particles. These particles would be zero-charge analogs to quarks. In today's universe, these particles would appear, along with gluons, only in hadron-like particles. These hadron-like particles would contain no charge and would measure as dark matter. In the 2J subfamily, the 1 particle, or J particle, would have spin 1 and 0 mass. One of its roles might associate with the Pauli exclusion force, which prevents pairs of fermions from occupying identical states. Regarding the G family, my work suggests not only a graviton, but also a spin 3 particle and a spin 4 particle. My work suggests a description for dark matter. People report ratios of dark matter effects to ordinary matter effects. Some inferred ratios of dark matter to ordinary matter pertain to galaxies. Hadron-like particles made of arcs and gluons might associate with people's notions of cold dark matter. However, it seems unlikely that these particles alone would suffice to explain inferred ratios of dark matter to ordinary matter. This chart shows ratios of dark matter to ordinary matter that people report. There might not be very many reports. but perhaps the results point to what might someday become seemingly prevalent approximate ratios. Some of the ratios are approximately ratios of integers. The first ratio, of densities of the universe, is some with more than 5 to 1. My modeling suggests bases for these ratios. My work suggests that nature includes so-called isomers of the set of all elementary particles except G-family particles. I associate, with each isomer, the stuff made from that isomer's elementary particles. The stuff associating with one isomer includes ordinary matter. I use the term isomer 0 to name this isomer. Isomer 0 includes some arc plus gluon hadron-like particles. Stuff made from isomer 0 arc plus gluon particles measures as dark matter. All of the stuff associating with the 5 additional isomers measures as dark matter. An isomer does not have its own copy of G-family elementary particles. To a first approximation, one might say that the stuff associating with each isomer includes the isomer's own photons. One might say that one instance of gravity connects the 6 isomers. The isomers can differ by how, for charged leptons, the generations match up with the masses. Stuff associating with 4 isomers, so-called isomers 1, 2, 4, and 5, evolves quickly into cold dark matter. So-called isomer 3 stuff evolves similarly to the stuff associating with the isomer that includes ordinary matter. These notions might suffice to explain ratios. The notions might suffice to explain other phenomena, including aspects of the Milky Way galaxy. This chart depicts, regarding densities of the universe, relative amounts of ordinary matter stuff and various components of dark matter stuff. For example, the chart gives a visual explanation for why the relative density of the universe for dark matter is somewhat more than 5 times the relative density of the universe for ordinary matter, namely, that the stuff associating with each isomer's arcs plus gluons measures as dark matter. To explain ratios of dark matter to ordinary matter, I need to provide information about my modeling. This information also provides perspective about my work regarding other topics, including elementary particles and cosmology. After discussing modeling, I return to the topic of dark matter ratios and proceed to topics in cosmology. The two-word term extant modeling denotes modeling that other people use. Extant modeling tends to describe motions of objects and changes to objects. The two-word term proposed modeling denotes new modeling that I suggest. Proposed modeling tends to describe properties of objects and properties of forces. Whereas much extant modeling has bases in mathematics pertaining to continuous functions, much proposed modeling has bases in so-called double-entry arithmetic. Double-entry arithmetic has similarities to double-entry bookkeeping. Adding a number to one side of an equation requires adding the same number to the other side of the equation. Proposed modeling does not necessarily depend on choosing between extant modeling models for motion. Proposed modeling discusses how to unite extant modeling and proposed modeling. Proposed modeling has a basis in the notion of isomers. Proposed modeling has a basis in the notion that long-range forces, or interactions mediated by G-family elementary particles, can model as having components. This notion has parallels to extant modeling in which an electromagnetic field models as including an electric field and a magnetic field. Extant modeling uses 2 harmonic oscillators to model a photon. Extant modeling tends to associate with 4 dimensions, 3 spatial and 1 temporal. Proposed modeling suggests 4 oscillator modeling for a photon. Here, in line with extant modeling, the third spatial oscillator cannot excite. This 4 oscillator modeling provides a starting point for developing much proposed modeling, including the notion of double-entry arithmetic. This chart features some proposed modeling components of 2G, or electromagnetism or photons, and of 4G, or gravity or gravitons. The components sigma g gamma are solutions to double-entry arithmetic equations. For example, 4G4 associates with, in many situations, most of gravity. For Newtonian modeling, 4G4 associates with an attractive force, with a monopole, or, radius to the -2 power, spatial dependence of force, and with a span of 6, as in 1 mostly ordinary matter and 5 all dark matter, isomers. If the source of the gravity rotates, 4G48 provides a next order adjustment. The word repulsive pertains. The word dipole pertains. I think that this component associates with, regarding general relativity, rotational frame dragging. Each of 3 instances of 4G48 has a span of 2, not 6 and not 1, isomers. The following remarks pertain regarding large-scale aspects regarding the evolution of the universe. Generally, dominant effects transit, over time, from effects that associate with 4G rows toward the bottom of the table to effects that associate with 4G rows closer to the top of the table. Similar changes in dominance occur, more quickly, on smaller scales. This chart shows solutions to double-entry arithmetic equations that associate with all of the elementary particles to which proposed modeling points. Each of the rows 2G through 8G associates with more than one solution. The parameter n sub eta0 associates with whether the relevant particles can model as not being entangled. Let's return to the topic of dark matter. Let's also discuss galaxy formation. This chart shows ratios of dark matter to ordinary matter that people report. Generally, my work seems to explain these results. My work associates with the 5+1 ratio of densities of the universe. Some observations pertain to galaxy clusters. One might suppose that the galaxy clusters are large enough to approximately reflect densities of the universe. One observation pertains to the depletion of cosmic microwave background radiation. People attribute half of the observed depletion to hyperfine interactions with ordinary matter hydrogen atoms. I suggest that the extra depletion might associate with isomer 3 hydrogen-like atoms. Regarding galaxies, people report various ratios. One paper aggregates results from studies of early galaxies, for example galaxies that associate with redshifts of around or more than 7. Observed earlier galaxies have ordinary matter stars and very little dark matter. Later galaxies have ordinary matter stars and more dark matter. Early on, 4G246 attraction, which has a span of 1, helped form ordinary matter clumps. Stars formed. Over time 4G48 repulsion drove away isomer 3 stuff and some isomer 0 stuff, while 4G4 attraction attracted cold dark matter that associates with isomers 1, 2, 4, and 5. That explanation comports with other observations of later galaxies, for which ratios approximate 4 to 1. Via a similar scenario, other isomers can form original clumps. If those isomers are not isomer 3, there is another path toward galaxies that exhibit ratios of 4 to 1. Via a similar scenario, my work suggests the possibility for galaxies that feature isomer 3 original clumps and little ordinary matter. There are reports of so-called dark matter galaxies. People observe ordinary matter stars and estimate a small non-zero density of ordinary matter. My work suggests an explanation for aspects regarding the rate of expansion of the universe and suggests eras that might precede the so-called inflationary epoch. This illustration suggests aspects regarding the evolution of the universe. The figure features notions pertaining to stuff that becomes large-scale objects. Throughout the evolution, objects move away from each other. After inflation, rates of separation decrease. After some billions of years, rates of separation increase. This chart shows some extant modeling notions regarding the rate of separation of neighboring clumps. As far as I know, no observations directly pertain to the would-be era of inflation or the existence of an inflaton. This chart shows results from proposed modeling. The results have bases in components of 4G and in elementary particles that I suggest. The chart suggests 2 eras that might precede inflation. The chart embraces the notion of an inflationary epoch. My work suggests an explanation for the notion that extant modeling seems to underestimate recent increases in the rate of separation of large clumps. Extant modeling might use modeling that, in effect, extrapolates from modeling that associates with the era of decreasing rate of separation. Proposed modeling associates the dominant effect for that past era with 4G246, or quadrupole, attraction. The span of an instance of 4G246 is one isomer. Proposed modeling associates the dominant effect for the current era of increasing rate of separation with 4G48, or dipole, repulsion. The span of an instance of 4G48 is two isomers. Proposed modeling suggests that the actual repulsion is, essentially, twice as much as extant modeling might suggest. Proposed modeling suggests other results and suggests possible ways to resolve some other instances in which observations and extant modeling might not agree. This slide suggests a relationship between two ratios. One ratio is, for two electrons, the ratio of electrostatic repulsion to gravitational attraction. The other ratio is that of the mass of the tauon, which is a charged lepton, to the mass of the electron, which is also a charged lepton. This relationship, along with other aspects of proposed modeling, suggests that charge and mass, or electromagnetism and gravity, might be more interrelated than extant modeling might suggest. My work suggests a formula that might interrelate the masses of the 9 known charged elementary fermions. The two charts show logarithms base 10, each of a mass divided by the mass of the electron. The leftmost chart might seem not to exhibit a useful pattern. The rightmost chart replaces information about quarks with information about geometric means of masses of pairs of quarks. This chart seems orderly, though, for each column, the increments between neighboring numbers are not uniform. I suggest that extrapolation based on the formula points to masses for neutrinos and for arcs. Also, from a perspective of modeling, the position of the tauon associates, at least indirectly, with differences in the evolutions of stuff associating with various isomers. This chart discusses suggested rest energies for elementary fermions. The chart omits the electron and muon. Those results are well known and are inputs into my formula that links the masses of the 9 known charged elementary fermions. My formula that might calculate the rest energy of the tauon produces the result that the chart shows. The standard deviation reflects the standard deviation regarding the gravitational constant. 8 standard deviations of calculated tauon rest energy fit within 1 standard deviation of measured tauon rest energy. I take the formula that links the masses of the 9 charged elementary fermions and extrapolate to suggest rest energies for arcs. For neutrinos, astrophysics suggests a range for the sum of the masses of the 3 neutrinos. My work can comport with that range in either one of two ways. One way is that all 3 neutrinos have a rest energy of about 3.4 times 10 to the minus 2 electron volts. Another way is that 2 neutrinos have that rest energy and 1 neutrino has a smaller rest energy, perhaps the number shown in the orange column or the number to the right of that column. Extant modeling might suggest excluding the former choice, but let's not discuss here making such a choice. This chart suggests a formula for the rest masses for elementary bosons other than G-family bosons. Each of the 4 terms seems to be quadratic in a parameter. For zero-mass bosons, the formula is exact. The best known non-zero mass, as of the year 2020, is that of the Z boson. Based on that mass, the formula predicts masses, for the Higgs and W bosons, that are, respectively, within 2 and 4 experimental standard deviations of the experimental nominal value. My work points to possible relationships between properties of objects. For example, the modeling suggests a relationship, for the tauon and electron, between charge and mass. My work suggests a catalog of properties of objects. Here the parameter lambda indexes properties, such as charge and mass, that the modeling associates with so-called spatial aspects. For lambda equals 2, 4, 6, and 8, lambda associates with twice the spin of a G-family force. The spatial aspects include notions related to isomers. In the chart, charge associates with lambda equals 2 and 14. Active gravitational energy associates with lambda equals 4 and 12. Angular momentum associates with lambda equals 8 and 10. For elementary fermions, generation associates with lambda equals 6. The chart shows symbols, I of I2 and I4, for isomers. For purposes of this presentation, the number I4 is 0. The number I2 associates with my numbering for the 6 isomers that this presentation discusses. The notion of non-zero I4 might associate with the dark energy stuff and with a possible explanation for dark energy density of the universe. Regarding lambda equals 0, the parameter n sub USA 0 pertains. For elementary fermions, n sub USA 0 associates with whether the particles have non-zero charge. For other objects, n sub USA 0 associates with whether the particles have non-zero mass. Similarly, lambda t indexes some properties, including, for quarks and arcs, color charge. For elementary particles, n sub UTA 0 associates with whether a particle can model as not entangled. People have opportunities to explain data. Let's look at some opportunities for which my work might offer bases for explanations. For most of these opportunities, the slides that I show suggest bases for explanations. Here are some opportunities related to elementary particles and small objects. An observation regarding hyperfine transitions regarding positronium suggests that extant theory might not adequately describe energy levels. People are producing and starting to study so-called polycrystals. People say that they do not understand the origin of baryony symmetry. My work might associate with a lack, in nature, of so-called magnetic monopoles. Here are some opportunities related to large-scale phenomena. For each of some large-scale clumping of stuff and some clumping of stuff within galaxy clusters, people report observations for which people say that extant modeling does not work adequately well. Here are some opportunities related to galaxies. People studied gravitational effects, associated with nearby galaxies, on components of individual galaxies. People report discrepancies between what they would expect, based on extant modeling, to observe and what they observe. Perhaps my notions of isomers and 4G components can provide some insight. People report observations of galaxies that seem to have stopped accruing matter. Maybe isomers and 4G48 repulsion can help explain a lack of further nearby material to accrue. People study aspects within the Milky Way. A study of so-called stellar stream GD1 and its dynamics suggests that there should be an object of a certain size that impacted the dynamics. People have not found the object. Given that I think that some isomer 3 dark matter objects are similar to ordinary matter objects, proposed modeling may offer an explanation. People study inhomogeneities regarding Milky Way dark matter. My notion of some similarities between some dark matter and ordinary matter might help here also. If you are viewing this presentation during a live seminar, a time for discussion may be about to begin. This presentation suggested advances regarding 2 sets of physics challenges. One set features describing elementary particles that people have yet to find and describing dark matter. One set features explaining cosmology and astrophysics data that people have yet to explain and predicting cosmology and astrophysics data that people have yet to obtain. My explanations regarding cosmology and astrophysics data offer the possibility that my descriptions of new particles and dark matter have merit. Compared to other attempts to address the challenges, the following notions seem to pertain. My work seems to feature more reuse of extant concepts and modeling. My modeling seems to feature simpler mathematics. My work seems to explain otherwise unexplained data. This presentation discussed highlights of my work. For further details and information, please feel free to look at my websites or to contact me. Thank you for your interest in the tiny and the vast, predictions about elementary particles, dark matter, and the cosmos.